Our next video here is on concentration units. Our learning targets in this video, there's a couple of them here. We want to be able to define and calculate the concentration units molarity, molality, and mole fraction. And we also want to be able to use those concentration units as conversion factors in other problems. Here you can see a list of resources, a video, and a couple of links to some practice problems that you could find on the internet. First of all, just want to ask the question, what is a concentration? We're going to give a definition here for that. Concentration. Whenever we talk about the concentration of a solution, very generally we are referring to how much of a solute there would be in that solution. So it is the amount of solute in solution. In case you've forgotten, I like to use the SOL apostrophe N as shorthand for solution. Some specific concentration units, the three we're going to look at today. The first one is molarity. Molarity. The abbreviation or the symbol for molarity is capital M. Molarity is defined as the ratio of the number of moles of solute per liter of solution. Moles of solute per liter of solution. So by definition, if we had 1 mole of a solute in 1 liter of solution, that would mean that we have a 1 molar solution. You see this 1 capital M, you would read that as 1 molar, and that's exactly what this tells us here, that we have 1 mole of solute per every liter of solution. Could mean half a mole of solute and half a liter of solution, but the ratio is 1 to 1. Alright, so let's see how this idea of molarity would apply to some of these example problems here. Let's take a look at example problem number 1. We're told that a 100.5 milliliter IV solution contains 5.10 grams of glucose, or C6H12O6, and it asks us to calculate the molar concentration of the glucose. Well, I know molar concentration, that is molarity, those two terms are synonymous there, so that means I need to find how many moles of glucose, C6H12O6, are there per every liter of the solution. That's what I'm looking for. Well, looking at the information given to us, we know that we have a certain mass of the glucose, the 5.10 grams. So I'm going to put that on top. And we can see that we're given a volume, 100.5 milliliters of the solution. If you notice how this compares to what we're looking for, we need moles of glucose on top, so I'm starting with the grams of glucose on top. We can just use a simple gram to mole conversion in order to do that. So if we have the molar mass of glucose, which happens to be 180.2 grams per mole, grams cancel, we're left in moles. Notice now our numerator units match what we're looking for. Now we still need to convert our milliliters into liters, so I can do that simply by saying that there are 1,000 milliliters of solution in every liter of solution. And now notice milliliters cancel, and our units now, moles of glucose per liter of solution, that's what we're looking for. Alright, plugging this into your calculator, you should get a value, 3 sig figs here. Your mass is going to limit you to 3 sig figs. I get 0.282 molar C6H12O6. Now you could write the unit as I've written it here with the capital M. You could also write the unit the way we wrote it over here when we started the problem. That would also be appropriate. Moles of glucose per liter of solution, they mean one and the same. Alright, next question, also dealing with molarity. How many milliliters of a 0.2 molar KMnO4, that's potassium permanganate, solution will you need if a lab procedure calls for 0.0500 moles of potassium permanganate. This is a little different than the last one because we're already given the molarity. Okay, we're asked specifically for how many milliliters. So how many milliliters of the solution would we need in order to get this 0.0500 moles of KMnO4? Now, this concentration is given to us, just like any concentration, that can always be used as a conversion factor. Okay, this here is a conversion factor. Recall that the molar ratio tells us that there would be 0.200 moles of KMnO4 in every liter of solution. So I can just use that as a conversion factor. Now, looking at the units that I have and what I want to get to, I know that moles need to go on the bottom or in the denominator of my conversion factor. So I'm going to put the 0.200 moles of potassium permanganate or KMnO4 in the denominator, and that is for every liter. Or you might just think, well, I want my answer in milliliters. So 1 liter would be 1,000 milliliters of solution. And moles of potassium permanganate cancel. We're left with milliliters, which is exactly what we're looking for. So we've done the problem. I believe we should get an answer here of 2.50 times 10 to the second, or that would be 250 milliliters. I wanted to write it in scientific notation, though, to show that I had 3 sig figs there. I'll finish it out here, milliliters of solution. And there's our answer. Alright, question or example number 3. And this is the last one dealing with molarity. We're asked, what mass of calcium hydroxide is needed to make 1.50 liters of a 0.25 molar calcium hydroxide solution? Alright, so we're asked for a mass. Now, it doesn't ask for a specific unit, so we could really pick any unit that we would like. Our most convenient unit would probably be grams. So I'll just say how many grams of calcium hydroxide would be equal to, and we have an option here of what value to start with. We can either start with 1.5 liters or the 0.25 molar. Now, the concentration can be used as a conversion factor, so I don't really want to start there generally. So I'll start with our 1.50 liters, and that is liters of solution. Okay, it's important to differentiate between the solution as a whole, which is what we have here, and the solute or the solvent specifically. Alright, so can I go straight from liters to grams? No, not really, because our conversion factor given to us, our molarity, relates moles and liters. So that's what I'll use that as. I know that a molarity of 0.25 molar means that for every liter of solution, there would be 0.250 moles of the solute, which in this case is the calcium hydroxide. So liters cancel. I'm into moles. Now we can just do a simple mole to gram conversion, which we're familiar with, in order to get our mass. Molar mass of calcium hydroxide is 74.09 grams calcium hydroxide per mole of calcium hydroxide. And our moles cancel. We're left in grams. Our 3 sig figs here, actually in this case, the sig figs, it's nothing we've actually measured yet because we haven't actually made this solution. We haven't actually measured this out. And in a case like this, and we might have learned this last year, talked about it last year, we really don't need to limit ourselves to any specific number of sig figs. I'm just going to go ahead and round it off to 3. When we actually go to make the solution, then we might actually be able to keep more sig figs, might end up with more than 3 sig figs based on our measurements that we take. And you can see here that we would get 27.8 grams for our answer. Alright, that is the last example problem with molarity. We're ready to move on to our next concentration unit, which is molality. I'm going to jump back up here to the key ideas and definitions. Molality is a concentration unit. First of all, that is spelled a lot like molarity. There's just one letter difference in it, L versus an R. And the value is often very close, but there is a difference. The symbol for molality is a lowercase m, so we have capital M for molarity, we have a lowercase m for molality. The ratio that it represents, and it is a ratio just like molarity, it is moles of solute, so that's just like molarity. But instead of comparing it to the whole solution, we are comparing it just to the solvent, and it is moles of solute per kilogram of solvent. Moles of solute per kilogram of solvent. And let's just jump straight down here to the example problem dealing with molality. And we're asked to determine, this is number 4, determine the molality of a sodium chloride solution made by dissolving 4.5 grams of sodium chloride in 100 grams of water. So we're asked to find the molality, so that means I need to find how many moles of solute, in this case NaCl, are there per kilogram of the solvent. Well, we're dissolving it in water, so our solvent is water. So my ratio I'm looking for is moles of solute, moles of sodium chloride per kilogram of water. Looking at the data given to us, we can see that we have 4.5 grams of sodium chloride. So I'm going to put that on top just because I know I can convert that into moles, grams into moles. And then we're given the fact that we have 100 grams of water, so I will put that in the denominator because I know I could just convert that from grams into kilograms. So I can see we really have two conversions here. We have a gram to mole conversion for the molality, so we just need the molar mass of the sodium chloride, which happens to be 58.4 grams NaCl per mole. NaCl. Grams cancel. We're left with moles. So that conversion I've done. I have moles in the numerator. And then I still need to convert from grams to kilograms, so I can do that here. There are 1,000 grams of water in every kilogram of water. And you notice our units now are moles of sodium chloride per kilogram of water, so that is exactly what we're looking for there. Sig figs here, it looks like we're going to get just 2 sig figs due to our 4.5 grams of sodium chloride. So I get 0.77 molal, that's a lowercase m, NaCl. Just like we talked about with the molarity, I could write it like this with a lowercase m, or I could write out the whole unit, if you will, moles of sodium chloride per kilogram of water, but that's not necessary because it is implied with our lowercase m there. All right, before we look at the other example problem with molality, one thing to mention here, you might be wondering, why do we need 2 concentration units that are so similar? We have molarity, going back up here to the key terms, molarity, moles of solute per liter of solution, molality, moles of solute per kilogram of solvent. They are oftentimes, especially if you have aqueous solutions, the concentrations are very, very close to each other. And that's just because the density of water is usually close to the density of the solution. Well, here's the reason why we have these different concentration units. And down here below, I'm just going to sketch a couple of quick pictures here. Say I had a 1 molar solution. 1 molar. Notice molar meaning molarity. Suppose I had that by having 1 liter of water, and in that there is 1 mole of solute. Doesn't matter what the solute is, just say I have 1 mole of solute that I've placed into this solution. Now this volume of water, and actually I just realized I made a mistake here. This should be 1 liter of solution, not 1 liter of water, because as we know, molarity is per liter of solution, not liter of water. Okay, so here's my solution. Now suppose I change the temperature of my solution. We know that any substance, whether it be a solid, a liquid, or a gas, its volume will be affected by the change in temperature. Now, for solids and liquids, generally not too much, but there is some effect. Let's say I heat it up. Okay, let's say I heat it up. I heat up my solution. Well, the liquid is probably going to expand. So I'm still going to have almost a liter. It'll actually just be slightly more. So it's going to be just a little bit greater than 1 liter of solution, and I still have 1 mole of solute there. Well, what happened to our concentration as far as the molarity is concerned? The molarity decreased because I still have 1 mole of solute, but now I have more than 1 liter of solution because the solution has expanded due to the increased temperature. Now, if I were talking about the molality, though, the molality would be unchanged because I still have 1 mole of solute, and I didn't add or subtract any solvent, so the mass of that would be the same. So the point here is the molality is not a function of temperature. So it doesn't matter what the temperature is, the molality will always be the same. The molarity is actually slightly affected by the temperature. So that's why we have different temperature concentration units there, so that the temperature doesn't have an effect if we don't want it to. All right, we do have one more example problem with the molality. It's on the back here. For me, it's a second page. You guys probably just have a front and back. So looking at our example here for the second problem with molality, we're asked what mass of barium hydroxide is needed to make a 1.25 molal, notice the lowercase m there, barium hydroxide solution containing 750 milliliters of water. So we're looking for a mass, and again, we could probably say that's going to be grams. So how many grams of BaOH2 would be equal to, or would we need, in order to make a solution? Here's our concentration. Again, that's a conversion factor, so I don't really want to start with that. So I'm going to start with our 750 milliliters of water. Alright, so we're asked to find the mass of the barium hydroxide. The first thing you might notice here is that the units might not match up to what you think we need, because we know that the ratio, on the molality is moles of solute per kilogram of solvent, and we're given a volume here. So we're going to need to know the density of water. Now, if you think back to last year, you'll probably remember the density of water is generally quoted as 1 gram per milliliter. I'm just going to use that, 1 gram of water per milliliter of water. It's not exactly 1 gram per milliliter, but it's really, really, really close, so we could probably just approximate that it is just 1. And now we can convert from grams to kilograms. There are 1,000 grams of water in every kilogram of water. And now we're in a position, because now we have our kilogram of solvent, that we can use our molality here. I know that in every kilogram of water, I will need to have 1.25 moles of the barium hydroxide, BaOH2, and now that we're in moles, we can convert to grams. So we need the molar mass of barium hydroxide, which happens to be, find it here on my sheet, it is 171.3 grams BaOH2 per mole. BaOH2. And moles cancel. We're left in grams. Our sig figs here. It looks like we are going to get 3 sig figs. Kind of like we talked about earlier, though, with making the solution. We actually haven't made this yet, so we really shouldn't let it limit us. I'll just go ahead and round to 3 sig figs, though. I get 161 grams barium hydroxide. And the lights just shut off. There we go. Alright, that was the last example with the molality. We have one more conversion factor to hit up. I'm going to go back to the key ideas. The conversion factor, not conversion factor, concentration unit. The concentration unit is mole fraction. And the concentration unit mole fraction is exactly what it sounds like. The symbol that we often use for mole fraction is a capital X. It is simply defined as the moles of A being whatever substance it is you want in the solution, divided by the total number of moles in the solution. That being everything, any solvents and any solutes, just add them together. That would be the total number of moles. So let's just go straight to the example that we have here. We are told that a mixture of gases contains 25 grams of oxygen and 35 grams of nitrogen. Determine the mole fraction of each gas in the sample. So let's just do the examples first, starting with oxygen. So I'm going to find the mole fraction of oxygen. Recall that that would be O2. It's diatomic gas. So that would be the moles of oxygen divided by the total moles, which is oxygen, plus the moles of nitrogen. Now, one thing you might notice is that we're given masses of these two. We're not given moles, so we're going to need to convert those to moles. So over here, we'll just show our gram to mole conversions. We have 25 grams of O2, and we need to convert that into moles of O2. So just use the molar mass, 32.00 grams of O2 for every mole of O2. So grams cancel, and I'll do the same thing for the nitrogen. I'll just do that down below here. We have 35.0 grams of nitrogen. The molar mass of nitrogen would be 28.02 grams of nitrogen per mole of nitrogen. Grams cancel. And we can figure out what those are. Let's see. I don't have those answers. Let me grab my calculator. I'm going to pull my calculator out here. Let's see. For the oxygen, we have 25 divided by 32. Looks like we get 0.78125. Now, I'm not going to round for sig figs here just because that's not really our final answer. I know we should have 3 sig figs. I'll keep that in mind when we get our answer here to the question. That's moles of O2, and for the nitrogen, we have 35 divided by 28.02. Same thing here. I should have just 3 sig figs of this calculation, but it's not really our final answer, so I'm just going to hold on to a few more, and we'll round at the end. All right, so there's the number of moles that we have of each. So now I can find the mole fraction of the oxygen simply by plugging it into our equation that we have over here. I can see the moles of oxygen. The mole fraction of oxygen would just be the total number of moles of oxygen, 0.78125 moles, divided by the total of the two. So I'm just going to add them together. 0.78125 plus the 1.2491. Now we said earlier that we should just have 3 sig figs. So once I get an answer to this, I'll just round that to 3 sig figs. So I have 0.78125 divided by the total, 0.78125 plus 1.2491. And I am getting here 0.385. I'm kind of running out of room here. I'll just put it down here. 0.385. That is the mole fraction of the oxygen. Notice here, it is a decimal. It will always be less than 1 unless there's only one substance in the mixture. In that case, it's not a mixture. If you wanted a mole percentage, you would just multiply this by 100. So if we multiplied by 100, we would see that 38.5% of the particles or the moles in this mixture are oxygen. For the nitrogen, we do the same thing, except we would just use the moles of nitrogen up here. I won't show the calculation, but if we just do the calculation here, it would be 1.2491 divided by the total. That will give us 61.5 for the mole fraction of the nitrogen. The mole fractions should always add to 1 or something really, really close to 1 because you always have to get to 100%. And in this case, you can see if you add those together, you will in fact get 1. Okay, that concludes all the example problems Now would be a good time if you want to pause and work these practice problems and then see if you get the right answer. I'm going to go ahead and work the practice problems now, but if you just want to pause it, try to work them yourself, and then go through the examples to see if you agree with what I got, that would be a great strategy. All right, practice problem number 1 here. It says a student dissolves 2.75 grams of sodium hydroxide in enough water to make 250 milliliters of solution. What is the molarity of the sodium hydroxide? The molarity, remember, the ratio is moles of solute, and in this case our solute is sodium hydroxide, moles of NaOH per liter of solution. That's what we're looking for. Since we want moles of sodium hydroxide on top, I'm going to put the grams of sodium hydroxide on top in our problem. And then for the liters of solution, we're given 250 milliliters of solution. If you just want to do that conversion in your head, you're more than welcome to. That would be 0.2500 liters of solution. You could just put 250 milliliters there and convert it to liters later if you wanted to. This might save you a little bit of time though. Alright, so we just need a molar mass then of the sodium hydroxide. Let's see, that would be 40.00 grams of sodium hydroxide per mole of sodium hydroxide. Grams cancel. Now notice our units. We are in moles of sodium hydroxide per liter of solution. That is molarity. Looks like we are going to get 3 sig figs. 2.75 is 3. So let's just plug that in here. 2.75 divided by 0.25 divided by 40. That gives us 0.275 molar for the concentration of the sodium hydroxide. All right, practice problem number 2. How many moles of hydrochloric acid are in 75 milliliters of a 0.35 molar hydrochloric acid solution? Well, we're asked for how many moles, so I'm just write that down. How many moles of HCl do we have? Again, we have a couple options here of where to start: a volume of the solution or a concentration. Concentrations, remember, are always conversion factors, so I don't really want to start there. You could. There actually is no specific order to do it in. But I generally think we have the most success when we don't start with the conversion factor. So starting with 75 milliliters of solution, now I can use my concentration as a conversion factor. I know that molarity, the capital M, means moles per liter. So in every liter of solution, or it could be 1,000 milliliters, I could write it that way too. That's convenient here because it will cancel our units. So in every 1,000 milliliters of solution, there will be 0.35 moles of hydrochloric acid. Notice our milliliter units cancel, and we're done with that problem. Just need to figure out what the answer is. Let's see, I believe we should get, looks like just 2 sig figs here because the 0.35 molar is just 2 sig figs. That gives us 0.026 moles of HCl. That's what we get there. Alright, 2 more practice problems here. Number 3, we're told 550.0 grams of an aqueous solution contain 25 grams of sodium phosphate. Calculate the molality of the solution. Remember, molality is moles of solute, and in this case our solute is the sodium phosphate in a 3PO4, for every kilogram of solvent. Now our solvent here is water. We're told it's aqueous. That means it's dissolved in water. So that's what we're looking for, moles of sodium phosphate per kilogram of water. Notice here, this 550 grams is not the mass of the sodium phosphate or of the water. It is the mass of the whole solution. But we're told that that 550 grams, of that, 25 grams of it are sodium phosphate. So the 25 grams of sodium phosphate, I'm going to put in the numerator, because we can just convert that into moles here. For the water, that should be the difference between the two, because the only things in the solution are water and the sodium phosphate. So 550 minus 25, that would give you 525 grams. I'll just show that calculation over here. We have 550.0 grams of solution minus the 25.0 grams of the sodium phosphate. That would leave then 525.0 grams to be water. So 525 grams, notice I want it in kilograms, so let's go ahead and do that conversion. That would be 0.5250 kilograms of water. And now I just need to do a gram to mole conversion. I recognize here I left off my gram unit there. So 25 grams, we need to convert that into moles. So we would just need a molar mass for the sodium phosphate, which happens to be 163.9 grams of sodium phosphate per every mole of sodium phosphate. So grams cancel, we're left with moles. Looks like we're going to get 3 sig figs, and I get 0.291 molal sodium phosphate. Alright, one more practice problem. This one is conceptually a little more difficult than the ones we've seen. It combines both molarity and molality. We're told that vinegar is a weak solution of acetic acid, CH3COOH. A particular vinegar solution has a concentration of 0.833 molar and a density of 1.006 grams per milliliter. Calculate the molality of the solution. Alright, so in the end we're looking for molality, so that again that is moles of solute, which is the acetic acid, CH3COOH, per kilogram of solvent. Well, we're told it's a solution, we're not really told it's dissolved in what, so we can assume that's water. Alright, you might be